I'm Howell J. Sigua, taking Bachelor of Science in Electronics Engineering at the University of Santo Tomas. Every year, around the world, about 500,000 people suffer a spinal cord injury. The majority of spinal cord injuries are due to unpreventable causes, such as road traffic crashes, falls, accidents in sports, or violence, which means it can happen to anyone. Symptoms of spinal cord injury depend on the severity of injury and its location on the spinal cord. Symptoms may include partial or complete loss of sensory function or motor control of arms, legs, and body. According to studies, people with SCI are 2 to 5 times more likely to die prematurely than people without SCI, with worse survival rates in low and middle income countries. Spinal cord injury is associated with lower rates of school enrollment and economic participation, and it carries substantial individual and societal cost. We want to propose a solution where the spinal cord injury patients will be able to control robotic assistive devices, such as robotic arms, by just imagining their intended arm movements. Our study investigates the possibility of developing a brain-computer interface that uses imagination of different arm movements. By using EEG, we record brain signals and use signal processing and machine learning techniques to decode, classify, and translate these signals into commands in controlling robotic assistive devices. Although many rehabilitation methods already exist, most of them does not provide the opportunity of independence, nor restore their same functionalities prior to the injury. Assistive technologies such as brain-computer interfaces offer the patients the opportunity to perform different daily tasks without the need for long-term rehabilitation. In motor imagery BCI systems, the brain signals are decoded and translated into useful commands that will then control the robotic assistive technology, such as robotic arms, allowing them to move and perform different daily tasks. But what is really the problem? Up to this date, most motor imagery BCI systems that are designed for upper limb control were only designed and tested on healthy-bodied subjects. This is due to the fact that SCI patients are very vulnerable and weak, and therefore they can stand long duration of experiments. And hence, it would be very impractical for them to undergo long series of experiments during the training of the machine learning models that will be used for the BCI system. However, several studies have shown that brain signals of healthy individuals and SCI patients have significant differences. And hence, applying these existing BCI systems to SCI patients may have significantly lower performance accuracy and may harm the patients. To address this issue, the use of convolutional neural networks has been proposed to improve the performance of such BCI systems. However, this method poses a challenge since CNNs requires a huge amount of training data, thereby requiring a large amount of training samples from SCI patients, which means that they must undergo several long and repetitive experiments. However, this is highly impractical and inconvenient for such patients. Hence, in our research study, we investigate whether the use of data transformation techniques together with hybrid-scale convolutional neural network or HSCNN model could allow us to record only few data from SCI patients and then create synthetic training data to compensate for the training of the CNN while maintaining a desirable degree of accuracy. Here, I show the overview of our research design and methodology. Our framework can be divided into 5 major stages: data acquisition, preprocessing, data augmentation, machine learning, and then performance evaluation for assessing the feasibility of translation into useful motor commands. Each phase will be discussed in more detail in the succeeding slides. For the data acquisition, EEG signals from 10 participants with subacute and chronic cervical spinal cord injury were recorded using 64-channel EEG device. The patients are between 20 to 69 years of age and all of them have restricted hand movements. Each of the participants sat in their wheelchairs in front of a computer screen with an arm resting on a pillow on their lap or on a table. They carried out the instructions given and attempted the movement requested on the computer screen. The participants were asked to focus their gaze firmly on the cross which was displayed during the whole trial of 5 seconds to avoid eye movements. They were also instructed to avoid swallowing and blinking their eyes during the trial period to avoid artifacts on the EEG signals. The class Q was displayed 2 seconds after the trial start for 3 seconds and correspond to one of 5 classes: pronation, supination, palmar grasp, lateral grasp, or hand open. Next is preprocessing. Signals were processed in MATLAB. We first removed noisy channels that were contaminated with perceptible noise. We also removed channel AFZ as it is sensitive to eye blinks and eye movements. Next, we removed stationary artifacts by filtering signals from 0.3 Hz to 70 Hz using a fourth-order Butterworth zero-phase bandpass filter. We reduced the data dimensionality using principal component analysis or PCA and retained the principal components explaining 99% of the variance of the data. We then computed independent components or ICs with the extended Infomax Independent Component Analysis or ICA. We then identified the ICs that are contaminated with muscle and eye-related artifacts, and then removed those ICs and projected the remaining ICs back to the original space. Next, and is probably the most important part of this study, is data augmentation. For a neural network, the classification accuracy is highly dependent on the amount of training data. When the amount of training data is limited, the classification accuracy is usually low. For motor imagery classification, it is difficult to acquire training data as each experiment has a complex procedure and strict rules to follow. To address this, we perform data augmentation to generate more training data from original training data. Our proposed data augmentation method can be divided into 3 stages. First is segmentation, where each trial is segmented into 3 crops. Next is time domain recombination, where the crops with the same labels are then recombined to generate new trials. For the same person in the same class, the crops at the same position from multiple trials are randomly swapped and recombined to generate recombined trials. Last step is frequency domain swapping. After the bandpass filtering, the filtered trials of the same frequency band are randomly swapped to form new filtered trials. Next is using machine learning to classify the hand movements. Here, we use hybrid scale convolutional neural network or HSCNN. CNN is a feed-forward network, and its structure is inspired by the visual cortex of the human brain. CNN generally consists of alternating convolution and pooling layers, and fully connected layers at the end. The convolution layer and the pooling layer are designed to extract features, while the fully connected layers are used for classification. The CNN network mainly mimics 3 important characteristics of the cerebral cortex: local connectivity, invariance to location, and invariance to local transition. The last stage is performance evaluation. We performed 10-fold cross-validation to avoid biasing, and then computed the overall classification accuracy. Now, we show our data and results. We compared the performance of our proposed BCI system with and without data augmentation. To the left is the confusion matrix of the classification without using data augmentation, and to the right is the one with data augmentation. Confusion matrices show the percentage of correct and incorrect classification of each class. Here, we observe the huge difference between the performances of the 2 systems. To summarize our results from 10-fold cross-validation, here we show the comparison between our proposed system and the one without data augmentation. And we also compared it to another state-of-the-art method called shrinkage linear discriminant analysis, or SLDA, with data augmentation. We show a significant difference and a very promising improvement in the performance of our proposed method over the others. And so to summarize, in this work, we have proposed a hybrid scale convolutional neural network architecture with integrated data augmentation, and thereby showed significant improvement in the accuracy of EEG motor imagery classification of hand movements for SCI patients. We also showed a significant improvement of up to 23.25% as compared to existing state-of-the-art method SLDA. Hence, our study creates a huge impact to the society, particularly those that are suffering from spinal cord injury. Our study helps increase the quality of life of SCI patients through assistive technologies such as brain-computer interface. It aims to provide motor assistance not only to SCI patients, but for all paralyzed patients. To date, our research is the first study that utilizes data augmentation in BCI motor control systems for SCI patients. And finally, our study is one step forward towards utilizing neurotechnologies in assisting patients with different disorders such as spinal cord injury and other motor impairments. At this point, I would also like to acknowledge my groupmates who all have contributed to the completion of our research and serve as my co-authors. I would also like to thank our research supervisor, Engineer Sigfred Prado, for mentoring, supervising, and guiding us throughout the whole project.